Welcome back. In today's lecture, we'll start a new topic, relaxation of the modeling rules. We have seen earlier that as we add the laws to any problem, for each law, a new pi number is added. Are there any situations where the number of laws from which the pi numbers are obtained are too many to be satisfied? In principle, as we add a law to be modeled, we add at least one uniquity parameter to be determined, and that should not cause any problem. But in actual practice, the situation is a little more complicated. The uniquity parameters are usually material properties, and it is not easy to tailor material properties to our requirements. To illustrate the point, let us consider a beam vibrating under the action of an oscillating force. There are three forces, basically three laws that we should worry about. The law of inertia, the inertial force is like mass into acceleration, and that gives you a pi 1 as Fi t square by rho L raised to power 4. Another is we have to worry about the elasticity of the material. Elastic force would be E times epsilon times L square. So that gives you a pi 2 is equal to Fe divided by E epsilon L square. The third force that we worry about is the force of internal damping. And we write in terms of energy loss per unit volume. And this is given as C into sigma raised to power 3, where C is a damping coefficient. And this translates into a pi number Cf square by L4. The deflection of the tip, or rather the amplitude of the deflection of the tip, is a function of F L rho E C, and the actual deflection is a function of time, the independent variables, and the independent parameters F, L, rho, E, and C. The three pi numbers that we obtained are these. Using scale factors F, L, and T, we can calculate the scale factors for density, elasticity, and the damping coefficient. K rho, the scale factor for density, turns out to be Kf Kt square divided by Kl raised to power 4 from the first one. For E, the elasticity, the scale factor is Kf divided by Kl squared. And for the damping, Kc is equal to Kl raised to power 4 divided by Kf squared. If we choose the model material to be same as the prototype material, the three scale factors are 1, all of them are 1, and then Kf is like Kl square and Kt is like Kl. But suppose the self weight of the beam was also significant. Then the weight would come into picture, and the gravity force Fg, which is like the volume times g, rho L cubed times g, gives you a fourth pi number Fg divided by rho L cube g. And for Kg is equal to 1, we work on Earth environment, we get Kf is equal to Kl cubed. Now, these conditions can all be satisfied only if Kt is equal to Kl is equal to Kf. All three are equal. It does not give us any freedom to do the experiments. So, what do we do? These considerations lead us to an important point in scale modeling. The more physical laws are involved in the phenomena, the more pi numbers are to be satisfied, and the less freedom exists in choosing the material and or the scale factors. Fortunately, conflicting claims on scale factors can frequently be resolved by what we call relaxation. It means the resolution of scaling conflict by using all prior knowledge of the phenomena to be scaled. Relaxations might consist, for instance, of neglecting less important laws or of infusing the experiment with analytical knowledge or even of dividing the whole phenomena into smaller and manageable parts. We have tried all of these strategies earlier, but now we will do them in a systematic manner. In an engineering problem, we begin with a selected and simplified part of nature, eliminating most of the marginal and non-essential laws to arrive at a useful approximation. Thus, even the full-scale test is often a relaxed version of the true event. But even then, we may find that we have too many laws and that scaling is difficult or impossible. When this happens, further relaxations are necessary. As a first step in relaxation, it is helpful to determine whether the laws causing scaling conflicts are governing the given system with equal or unequal strengths. If they are of unequal strengths, the weakest laws can be disregarded within segments of the investigation, if not throughout its entire range. Emory Shearing gives a summary of the various relaxation techniques in modeling requirements. Is divided into two parts. First, when the phenomenon governed is by law of unequal strength, and on the right are the strategies used when the phenomenon governed are by laws of unequal strength. When the laws are of unequal strength, the strategy is the neglect of weak laws, and this neglect of weak law could be throughout the entire range of the investigation or within the segments of the investigation. And when we neglect it within segments of the investigation, the segmentation could be temporal or could be spatial. In temporal segmentation, we do sequential modeling. In spatial segmentation, we could adopt regional modeling or directional modeling. When the phenomena governed by laws of equal strength, then we run into a little problem and we have to be more innovative. One of the technique is when we restrict the generality. We look at some region where we could neglect the law, if not throughout. We could simulate the law by using dummy weights, by using dummy springs, or by fixing transition. Some of the techniques we will discuss later. We could also adopt restriction of the gross effects, spatial or temporal. And of course, the always available technique of use of analytical knowledge. Or we could work with the same material which may restrict the range of scale factors that we can use. First, we'll talk about what we mean by strength of laws. Let us suppose that a phenomenon is controlled by three pi numbers, pi 1, pi 2, and pi 3. Let's study the variation of pi 3 with pi 1 for constant values of pi 2. If the behavior of pi 3 with respect to pi 1 is as shown by these broken lines, this means this is a weak law. We could neglect pi 3 throughout this region. Or the behavior could be like this, the solid line. Here we see the effect of variation of pi 1 on pi 3 is large. So we cannot neglect the effect of pi 1. Pi 1 is a strong law. Another possibility is the behavior is like this. In that case, we see that over this range of pi 1, the effect of pi 1 is small. Pi 1 represents a weak law in this region of the values of pi 1. But on this side, the strength of the law is not negligible, and we need to worry about pi 1. So if we are doing segmented modeling, we could neglect pi 1 over this range, but not over this range. Let's give some examples. We had considered the flow of fluid in a pipe. 3 force laws are important: inertia, viscous, and pressure. As we have done a number of times, we can write the pi numbers for these 3 forces. The pi number that results from the inertia forces is Fi divided by rho L square V squared. The pi number that results from viscous forces is like F mu divided by mu V L. Mu is the viscosity. And from pressure, we get the pi number Fp divided by delta P L square. Of course, we have geometric similarity parameters L by D and epsilon by D. Epsilon is the roughness parameter. Epsilon by D is the relative roughness parameter. L is the length of the pipe and D is the diameter of the pipe. From the first 2 laws, inertia and viscous, we get Reynolds number rho L V divided by mu. And from the first and third law, we get the Euler number delta P divided by rho V square. We treat delta P as a dependent parameter. So the Euler number is a dependent parameter, and we can write the functional relationship as Euler number is equal to delta P divided by rho V square is a function of Reynolds number L by D and epsilon by D. And this can be rewritten as delta P is equal to 1/2 rho V squared into L by D, a function F of Reynolds number and epsilon by D. F is called the friction factor for the pipes. We had obtained this equation earlier. Now, this function F as a function of Reynolds number, and the relative roughness parameter epsilon by d has been plotted by Moody in the Moody chart to obtain this relation. On this, the friction factor F is on this scale, the Reynolds number is on this scale, and the various curves are for the various values of the relative roughness parameter epsilon by d. Now, notice in this case, epsilon by d does not occur. This is true for all values of epsilon by d. Since F is a ratio of the representative pressure force to the representative inertial force, Reynolds number the ratio of the representative inertial force to the representative viscous force, the relationship of F proportional to 1 over Re, as is denoted by this straight line sloping down, valid in the low Reynolds number range, means that the representative pressure force becomes proportional to the representative viscous forces, and hence the influence of inertia is negligible. So, for modeling this laminar flow, we could neglect the inertia force completely. The result is obtained by balancing the pressure force with viscous force alone. In the other limit, for larger Reynolds number, in this gray area, the friction factor seems to be independent of the Reynolds number and just a function of epsilon by d, the relative roughness parameter. So, this is the region where viscous forces could be neglected and the pressure forces are being balanced by the inertial forces alone. So, we have used two approximations: neglect of inertial forces in the low Reynolds number region and neglect of viscous forces in the high Reynolds number region. Let's revisit the wind tunnel testing of aircrafts and aircraft components. A wind or the air blows at large speeds in a tunnel. The aircraft or aircraft model is kept within the tunnel, and forces that the air applied on this model are measured, and from this, prediction of the forces on the full-scale aircraft are obtained. The forces of interest are the inertial, viscous, and compressibility forces in the air. The scale factor for the inertial force is like K rho, Kv square, KL square, obtained a number of times throughout this course. The scale factor for the viscous force is K mu, Kv, Kl, also obtained a number of times in this course. And the scale factor for the compressibility forces, Kfc, is like K of Es, the elasticity of the material, times Kl square, the area. And the elasticity of the material, compressible gas, can be written as K rho, Ka square, K gamma, where A is the speed of sound in that material, times Kl square. Gamma is the ratio of the specific heats, Cp divided by Cv. From the first two, of course, we obtain Kv is equal to K mu divided by K rho Kl. The first two, when we equate them, results in Reynolds number, and from the Reynolds number, we find that the scale factor velocity must be like scale factor for K mu divided by scale factors of K rho and scale factors for length. And from the first and third, that is inertial and compressibility forces, we find Kv as Ka divided under root K gamma, which can be written as Kr star, where R star is the gas constant, times K theta, where theta is the absolute temperature of the gas. So these are the two laws that we obtain for modeling. Kv is equal to K mu divided by K rho KL, and Kv is equal to under root Kr star times K theta. Now, notice that if we use the same gas, that is, we use air at standard temperature, the material properties are same. So K mu, K rho, Kr star and K theta are all 1. So second of these relations gives you Kv is equal to 1. And if K is 1, then the first relation dictates that Kl must be 1. So this rules out the possibility of testing scaled model in the wind tunnel using the normal atmospheric air. Is there a way out? Yes, there is a way out if we could modify K mu divided by K rho. If we pressurize the gas, if we pressurize the atmospheric air so that the density increases, the viscosity mu does not increase appreciably or does not change appreciably, even when we increase the density by a factor of 10 or so. So that as you pressurize the gas, K rho increases and the kinematic viscosity decreases. So K mu by K rho becomes much larger than 1. And so that permits us to obtain a KL which is smaller. So one way to test models at the same value of Reynolds number and Mach number is to test them in what is called the high density tunnels. This is NASA's high density tunnel, which has now been decommissioned. Is a large vessel inside which the pressurized air is kept with a pressure of about 10 atmosphere. So the density is 10 times. And so we can work with the scale model of KL is equal to 10. That is 1/10 the full scale model. This was one facility that could be used for testing the components at the same value of Reynolds number as the actual prototype. There's more to it. If we study the drag coefficients of different bodies and as they change with Mach number, we see curves like this for a cylinder, for a sphere, for a round nose projectile and for a sharp nose projectile. And the important thing to note is this region where the drag coefficient is quite independent of the Mach number. This permits us to ignore the compressibility effects for Mach number below a value of 0.3 or 0.4. So if we remain below 0.3 or 0.4, we could ignore the effect of the Mach number. So we can work with only two forces, inertial forces and viscous forces. Further, if we study the drag coefficient of a body, here a smooth sphere, and we study the variation of drag coefficient with Reynolds number, we can see this variation. Obviously, this region where the drag coefficient varies inversely with Reynolds number is a region where inertial effects could be neglected. Low Reynolds number region, and we had covered this in quite a bit of details earlier. But the interesting thing to note is this region where the drag coefficient is independent of the Reynolds number. First, over this range from 10 raised to the power 4 to about 3 into 10 raised to the power 5, CD is constant. Then, again at a much larger value. We had seen in a fluid dynamics course that the first region represents the region of laminar separation around the smooth cylinder. And the second is when the boundary layer is turbulent. So there's turbulent separation. But the Reynolds number is constant. Since most of the flows in aerodynamics are high Reynolds number flow in which we are interested. So, postulating that the drag coefficient is independent of Reynolds number on the aerodynamic body is often made assumption. So we use the relaxation that viscous effects could be neglected and the drag force is governed largely by pressure forces and inertia forces. It is interesting to see that the lift coefficient of NACA 4412 aerofoil for various Reynolds number established the truth of this. These three curves, this, and this, they cover a Reynolds number range from 75,000 to 3 million. A very large range. Most flights are within this range. And over this region of alpha, the three curves are almost coinciding. Again confirming the fact that the lift coefficient is quite independent of Reynolds number in this range of Reynolds number. So that simplifies the testing of models in wind tunnel. For large enough Reynolds number, we don't worry about Reynolds number at all. We neglect the viscous law. We take a model of the aircraft or the aircraft component, put it in the wind tunnel, or run the test at a large enough Reynolds number so that we are within this range of Reynolds number. And then the coefficients, drag coefficient, lift coefficient, moment coefficient that you obtain can be used to predict the forces on moment on the prototype. So all wind tunnel testing, or rather major wind tunnel testing, is quite independent of Reynolds number. Other applications of this neglect or weak loss are the neglect of radiation in low temperature heat transfer applications. There's radiation in almost every situation, but in low temperature heat transfer applications, when I say low temperature, I mean even up to 300 degrees Celsius. We do not worry about radiation effects. Similarly, neglect of gravity in the vibration of lightweight structure. The self-weight of structure is almost never considered. When structures are light, the weight of submicroscopic particles in colloidal materials is also neglected. Surface tension effects in opal channel flows are not considered. This is an important application, and we'll consider this later in more details, particularly because it exposes a new paradigm. There are situations when surface tension is negligible in the prototype, but could have serious applications in the model if the model is not made carefully. We'll discuss this later. How do we discover weak laws? Self-modeling is one of the techniques. In self-modeling, the prototype itself becomes the model so that the length scale factor as well as the scale factors for all the material property parameters are unity. Any quantity other than length and the material properties, however, can be changed. Self-modeling experiments are frequently used in fundamental heat and mass transfer experiments to clarify the influence of certain laws whose parameters can be varied without affecting the length and material properties. A great number of weak laws can be identified through self-modeling. Self-modeling test often permits us to establish the governing laws of a given machinery. We'll discuss this to a hydrodynamic torque converter. Hydrodynamic torque converter is used to transmit power from an IC engine to the wheels without the use of a conventional gearbox. Here, the casing of the torque converter is connected to the flywheel of the engine. So this is where the input power goes. The whole thing rotates. This portion works like a pump. There is a hydraulic fluid inside, and as the casing rotates with the vanes, it acts like a pump and pumps the fluid to the left into the turbine section, which makes the turbine part rotate, and the power output is available on this shaft. Such a transmission is principally governed by inertial forces of both the working fluid and the moving mechanical parts. Viscous forces appear to be negligible because the flow in the hydraulic circuit is thought to be turbulent. Is this assumption correct? The correctness of this assumption is to be verified in a self-modeling test. So two forces of importance. If the viscous forces are not negligible, inertial forces like MA which gives you rho L raised to power 4 omega squared, where omega is the angular velocity, and the viscous forces, which are like mu times L square divided by omega. It is understood that all quantities are the characteristic values. Converting these forces into torque, the inertial torque would be like rho L raised to power 5 times omega square, multiplying the force by L. The viscous torque would be like mu times L cube by omega. For self-modeling tests then, where the length scale is 1 and all the material properties are the same, so that the inertial force requirement will give you T, the torque divided by omega square is constant, and the viscous forces would give the requirement that torque divided by omega is constant. Two quite different things. Now we will run the test on the torque converters for various values of omega and various values of torque. Input torque and the output torque. Input rotation omega 1 and output rotation omega 2. And if we plot the curves against T1 divided by omega 1 square, the pump side value of torque and omega. The value of omega 2 by omega 1 and the value of T1 by T2 are obtained as these. At various omega 1s and the various values of T1. What does this show? This shows that T divided by omega square is constant, is the correct modeling rule for the self-modeling test. That means that the torque converter is governed by inertial forces, and we can forget about the viscous forces. So the assumption of negligible viscous forces, because the flow is expected to be turbulent within the casing of the torque converters, stands the test of self-similarity. Thank you.